All right, calculus students, here comes the second video to help you get ready for the Fall Common Assessment this year. This question is the second question from last year's Fall Common Assessments. This was question 2. This question is calculator inactive, and it is a great sort of combination of skills that we've been studying so far. And just like in the first video, parts of this question were presented to both the AB and BC students last year, and then there's a part that was just for the AB students, and then there's a part that was just for the BC students. So we'll look at all of those parts, and I'll let you know which part's which. So let's get started. The function g is defined by this piecewise function, g of x equals 3x squared plus 2x for x less than or equal to 0, and e to the 2x for x greater than 0. Okay, pretty standard. We've got two different pieces. We have our domain restrictions, pretty friendly functions to work with at this point in where we are in a calculus class. And the first question, and this is for both AB and BC students, is a question of whether or not g is continuous at x equals 0, and then we have to justify our answer. And so things to keep in mind is that when we're looking to justify continuity, there's always three pieces, and we have to get the notation correct. If you want to demonstrate or check out continuity of a function at a point, you need to find the value of the function at that point, and notation is going to be really important here. You're going to have to evaluate the value of the limit at that point, and because we have a piecewise function, and our piecewise function is defined differently on the left and on the right of 0, this computation is actually two pieces. We're going to have to look at limit as x approaches 0 from the left, and we're going to have to look at the limit as x approaches 0 from the right. And we need those two pieces to be equal to each other for the limit to exist. And finally, the third piece is to show that the limit as x approaches 0 is equal to the value of the function at 0. We need all of this to be true in order to demonstrate that g is continuous at a point. If any of these things is not true, then we can declare that g is not going to be continuous at the point. Well, let's get started. Okay, g of 0. Well, the value of g at x equals 0, you've got to determine which piece of the function to work with. Since x is equal to 0, we use the top piece. That's 3 times 0 squared plus 2 times 0. Well, that's 0. Okay. We're going to find the limit as x approaches 0 from the left. Well, if we're approaching 0 from the left, that means numbers smaller than 0. We're talking about negative numbers. Those values are less than or equal to 0, so we use the top piece. I need to find the value of the limit as x approaches 0 from the left of 3x squared plus 2x. Because this is a polynomial, that means it's a continuous function. 3x squared plus 2x is continuous. I can evaluate the limit by simply plugging in 3 times 0 squared plus 2 times 0, and we get 0. Sorry that we're kind of crowding the space here. Now let's look at the limit as x approaches 0 from the right. If I'm approaching 0 from the right, those are values of x greater than 0. I use the next function. So limit as x approaches 0 from the right of e to the 2x plus 2. Well, e to the 2x is a continuous function. Adding 2 to it maintains its continuity. So I can evaluate the limit by simply plugging in. I get e to the 0 plus 2. That's 1 plus 2, which is 3. Well, look what just happened. The limit from the left of 0 is 0. The limit from the right of 0 is 3. Because these two are not equal to each other, the limit as x approaches 0 doesn't exist, and the function isn't going to be continuous. Now you're going to have to write that up, and we're going to say something like Since the limit as x approaches 0 from the left of g of x is not equal to the limit as x approaches 0 from the right of g of x, this means g is not continuous. Be specific. G is not continuous at x equals 0. This was worth 2 points. 1 point was for, we said, considering the value of the limits from the left and the right. So you found the limits on the left and the right, or you attempted to find the limits on the left and the right. We awarded 1 point. That was a rather kind point. And then the second point comes in for your conclusion based on the work that you had here. So altogether, that was worth 2 points for part A. It's a pretty standard question. I would expect something like this to show up on nearly every AP exam that you're going to take, including the fall common assessments. All right, let's keep going. Part B, again, A, B, and BC students here need to find g prime of -2 and g double prime of 3. To find g prime of -2, this is always going to be a two-step process. My value of x is less than 0, so I'm going to use the top function. I know that g of x is 3x squared plus 2x. I want to be careful with my notation here. G prime, take a derivative, is 6x plus 2. Nice and easy. Now evaluate g prime at -2. You get 6 times -2 plus 2. You could stop here if you'd like, or you could multiply this out. -12 plus 2 is -10. G prime of -2 equals -10. Easy peasy. To find g double prime of 3, well, here the x value is positive. And the reason that I'm stopping to think about the value that I'm evaluating the derivative at, whether it's greater than 0 or less than 0, is that that's where my function changes. So I know that for x greater than 0, g of x is e to the 2x plus 2. I need to find the second derivative. So I find g prime, that'll be e to the 2x times 2. That's because of a chain rule. I'll rewrite this as 2e to the 2x. G double prime, take the derivative of the derivative. Well, that's 2 times e to the 2x times 2 again because of the chain rule. So g double prime of 3 is 2. E to the 2 times 3 is 6 times 2, which is 4e to the 6th power. That's g double prime of 3. Part B is worth 2 points. 1 point for the derivative of g at -2. 1 point for the second derivative of g at 3. Be careful that you don't make any mistakes in your notation. A big mistake students would make is they'd say g of x equals e to the 2x, and then say something like g prime of 3 equals 2e to the 2x. Look, you only evaluate your first derivative or your second derivative at that numerical value in the very last step. Everything else, g prime of x, g double prime of x, and finally in that last step, g double prime of 3. Be careful. That's called a linkage error, and that is a place for students to lose points on the AP exam. All right, let's look at part C. Also for both A, B, and BC students. Here we need to find g prime of 0 or explain why this value doesn't exist. Well, let's stop and think about that. The common mistake students would make is they'd say, oh, well, g prime of 0, I just need to find the derivative of g at 0. They'd go up to the original function and say, oh, it must be the top piece. Let me find the derivative and evaluate at 0. What you're forgetting about is that in order for a derivative to exist, in order to find the derivative of g at 0, the function has to first be continuous at that point. And we showed in part A that g is not continuous at 0. So all you needed to say is that since g is not continuous at x equals 0, g prime of 0 does not exist. That's it. That statement, that's all you needed right there. That got you the 1 point you want to get in and get out and get done. All right, let's keep going. In part D, can the this is part D. This was for the AB students only. Can the intermediate value theorem be applied to g of x on the interval -2 to 2? Okay, we're going to pause right there. All right, let's keep going. There was a little bit of a glitch there. Sorry about that. Okay, so let's keep going. We're still working with the same function, and now we're going to look at part D, and this was part D that was for the AB students only. Can the intermediate value theorem be applied to g of x on the interval -2 to 2 to prove that there must be a value of c such that g of c equals 10 at least once, and then we need to justify your decision? Well, intermediate value theorem, that is a theorem you should be familiar with at this point. And the intermediate value theorem, there is a condition that has to be true in order to use the intermediate value theorem, and that condition is the condition of continuity. So the question you need to ask yourself is g a continuous function on the interval -2 to 2? And if you think about that for just a second, you should already know the answer. We've talked about this in part A. It came up again in part C. What we know is that g is not continuous. Wow, that was a bad spelling of continuous. Good thing they don't charge you for spelling. G is not continuous at x equals 0, which means the IVT cannot be applied on the interval -2 to 2. Now, had we picked a different interval, if the interval didn't include x equals 0, then you might be able to use the IVT as long as the function was continuous on the entire interval. But since x equals 0, we've already shown the function's not continuous. I can't use the IVT on this interval. This was also another 1 point kind of question. Really just testing, do you understand your definitions? IVT is a really popular theorem. Okay, let's move on to part D for the BC students. Now, this is only for the BC students. If you're in AB, feel free to skip over and skip ahead in the video and wait for me to come back to part E. But for the BC students, here we go. For values of x greater than 0, g is a differentiable function. They're telling you g is differentiable, which means that g is also continuous. Okay, you get that for free. For the interval 0, 4, determine the value of c guaranteed by the mean value theorem. Okay, so g is differentiable, which means it's also continuous. So for the interval 0 to 4, determine the value of c guaranteed by the mean value theorem. Okay, I'm not in love with the phrasing on this question because we've already established that the function is not continuous at x equals 0. And if you're not continuous at x equals 0, your function can't be differentiable. Okay, so here's what should have happened. I should have redefined the function as e to the 2x plus 2 for x greater than or equal to 0. That's something that got past all of us last year. Okay, so we are redefining the function as g of x equals e to the 2x plus 2 for x greater than or equal to 0. This is an oversight that I missed last year. My apologies for that, but let's just do this. What the MVT says is that if you have a function that is differentiable on the open interval, continuous on the closed interval, then if I find g of 4 minus g of 0 over 4 minus 0, that is your average rate of change, that is your slope of the tangent line, then there has to be a value of c such that g prime of c is equal to this value. And that value of c will have to be between 0 and 4. That's what the mean value theorem promises. So we'll say something like, since g is continuous on 0, 4, which it really wasn't until we redefined it, and differentiable on the open interval 0, 4, there exists a value of c in the open interval 0 less than c less than 4, such that g prime of c equals g of 4 minus g of 0 over 4 minus 0. Well, what's g of 4? G of 4 is going to be e to the 8th plus 2 minus g of 0, e to the 0 plus 2 over 4 minus 0. So that means g prime of c is equal to e to the 8th minus e to the 0 is 1 over 4. In this problem, they actually want us to determine the value of c guaranteed by the mean value theorem. That means we're actually going to have to solve this equation. So g of x, well, what's g of x? We said g of x is e to the 2x plus 2. G prime of x is 2e to the 2x. I'm looking for the value of c that's going to make the derivative have a value of e to the 8th minus 1 all over 4. So I need 2e to the 2x to be equal e to the 8th minus 1 over 4. And I'm going to solve this equation for x. So we're going to divide both sides by 2, or multiply it by half if you prefer. E to the 2x will be e to the 8th minus 1 over 8. To get to the x, I'm going to take the natural log on both sides. Natural log here, natural log there. The natural log of e to the power is just going to be 2 to the x. Natural log of e to the 8th minus 1 over 8. Solving this equation, we get that x will be 1/2 the natural log of e to the 8th minus 1 all over 8. That is the c value that we're looking for. So I'd say something like c is equal to 1/2 the natural log of e to the 8th minus 1 all over 8. That's the value that's guaranteed by the mean value theorem. And the way we awarded a point is we awarded 1 point for this ratio here, the g of 4 minus g of 0 over 4 minus 0. Getting to here was 1 point. Then setting up the equation 2e to the 2x e to the 8th minus 1 over 4 earned you a second point. And then going through the algebraic maneuverings to solve for the value of c earned you the final point. So this was worth 3 points. All right, one last part, and this part is for both the AB and the BC students. So here we go. Okay, part E. For x greater than 0, a new curve is defined as the natural log of x times the cosine of y equals y. Using this information, find dy dx in terms of x and y. So the natural log of x times the cosine of y is equal to y, and we want to find dy dx. We want to find the derivative of y with respect to x. Well, look at this. You've got natural log of x times the cosine of y equals y. You've got the x's and the y's mixed in together on the same side of the equation, and you want to find the derivative. This technique is called implicit differentiation. And by this point, we've already studied it in both courses. The way that this works is we are going to take the derivative of the entire equation, the left-hand side and the right-hand side, and we're going to have to be careful because we're taking the derivative with respect to x. And that means anytime you get to an expression that involves a y, if you're taking the derivative, you're going to have to use the chain rule. So let's see, I've got natural log of x times cosine of y. That's a product rule when I take the derivative. And the product rule says take the derivative of the first. Derivative of natural log of x is 1 over x, times, leave the second one alone, that's your cosine of y, plus the natural log of x times the derivative of cosine of y. And the derivative of cosine of y is negative the sine of y times dy dx because of your chain rule. You just took the derivative of an expression involving y, but you're taking the derivative with respect to x. Now don't forget to finish this off. You have to take the derivative of y, and the derivative of y is 1 dy dx. Okay, so far so good. The goal now is to solve the equation for dy dx, and I see dy dx showing up on both sides of the equation. The algebra move that you need is the terms that have dy dx need to be on one side of the equation. The term that doesn't involve the dy dx, we're going to move to the other side of the equation. So what are we going to do? I see this natural log of x times negative sine of y dy dx on the left. I see the 1 dy dx on the right. I want to move this guy over, and I want to move the 1 over x times cosine of y to that side. So my new expression will be negative natural log of x times sine y dy dx is equal to, minus 1 dy dx, because I'm subtracting the 1 dy dx to the other side, is equal to the negative of 1 over x times the cosine of y. Now there's too many negatives in this, so I'm just going to multiply both sides by negative 1 to get the natural log of x times sine y dy dx plus 1 dy dx equals 1 over x times the cosine of y. I have my two terms that both have the dy dx. That's a common factor. I'm going to factor out the dy dx to get the natural log of x times sine of y plus 1 equals 1 over x times the cosine of y. To get dy dx by itself, it's just a division move. I'm going to divide both sides by this whole expression. So I'll have 1 over x cosine of y divided by natural log of x sine of y plus 1. And there's lots of algebraic things that you could do to simplify that expression further, but there is absolutely no need to do that. What did we do? We awarded 1 point if you knew to use the product rule, if you use the product rule appropriately, and then 1 point for proper use of the chain rule. So basically 2 points if you found the derivative correctly. And then another point if you solved for dy dx, for a grand total of 3 points. Anyway, that wraps up that question for both the AB and the BC students. I hope you found this to be helpful, and this should be really good, strong study material for you as you get ready for this year's Common Assessments. Good luck!